Experiments in Physics with Dr. Frank Oppenheimer. A brief demonstration of the equipment used in the Library of Experiments in Physics, produced in cooperation with University of Colorado Television. Today's experiment.
This experiment on the telescope sets up a very simple telescope with an objective lens and an eyepiece. One can measure the positions of these on a scale and study the various properties of a telescope. First of all, the geometrical optics properties, which depend on the image and object distances. One can locate the real image produced by the objective on a screen, which can be placed here, and one can put an aperture in front of the objective lens, which can be, whose size can be changed, and one can study the effect of the aperture on the quality of the image, and one can make that small enough so that actually the resolution due to the wave nature of light becomes so poor that one gets a rather poor quality image, and that way can measure the wavelength of light. This can be set in front of the objective lens. There's a little hook on the bottom here that catches on the rail, and it can be just mounted with this screw open to sit there. The object that one's looking at would be a light bulb, which is over there, and one can change the intensity of that light bulb with a variac. You should be able to see that intensity going up and down as one does that. Now I'm turning the intensity down, and now I'm turning it up. It's quite low now. The first thing that one has to do is make fairly careful adjustments so that the optic axis is perpendicular to the lenses. That's done by, most conveniently, by leveling the optical bench, looking down on the lens and making sure that its plane is perpendicular to that of the optical bench, and then getting the height of the lens above the floor, which is usually best done in 2 steps, measuring that height to the center of the lens here, and then measuring the height of the table, and then adjusting the height of the bulb so that it's exactly the same height as the center of the lens from the floor. I simply come over here and I measure the height of the bulb. While I'm over here, I can also measure the length of the filament with a little more delicate ruler than this in centimeters, and then count the number of turns so that I know the spacing between the centers of the turns of the 30 or so coils that occur over the length of the bulb. By knowing the total length and the total number, I can find the distance between, and I should examine this to see if that's divided between, how the spacing is divided between the wire size and the coil size. That's best done by having the variac extremely dim so that the wires merely glow and don't blind one at all. Having set that up, then I can turn up the intensity, and I can take the eyepiece off, and I can set up a screen to look at the real image produced by that lens. That, of course, will be quite small. In order to see that, I will need more intensity of the light bulb. And I'll look in here, and I'll see a spot, and I'll move the telescope back and forth just a little bit to get that absolutely centered in the screen here, and adjust the height of this, and then I will move this back and forth to get a good image. It's most convenient if one keeps the eyepiece near one end so one can get one's head in and adjust the position of the objective so that it's roughly in the right place. I can also, of course, focus by moving the objective. Let's just have a look at that on the television screen. There's a camera here which takes the place of my eye and sees exactly what my eye would see, perhaps with a different magnification. And as I move this back and forth, you can see the real image on the screen here. You're seeing the ground glass screen. You can see how that real image blurs and comes to a sharp focus. That real image, of course, I could see also if I was looking at it with my eye, but I can't look at it directly with my eye very close here any more than I can see my finger close. But if I stood back where the camera is, at least with my eye at least 25 or 30 centimeters from there, I should see the real image. Let's see what happens when I do that with the camera. It's too bright. I'll turn the intensity down. And now the camera is looking at the same real image that it saw when I was looking at the screen. There's the image it sees on the screen. Having done that, I can now use a simple magnifier, which is the eyepiece, and examine that same image. I'll put that in here, and I'll focus until I see clearly the graininess of the frosted glass, and at that point, if the image was sharp on the screen, it should be also a maximum sharpness. And what I see in there is a very colored image due to the chromatic aberration of the lens. When I think we could actually look through the lens now and perhaps see some of the same thing. Can we focus that a little better to see what the lens will see? And there is what the lens sees, and you notice it's not a very good image. Let me get it centered just a little bit better in that screen. And because the frosted glass blurs the image a little bit. However, when I take the frosted glass out, now I'm going to look through, I see that it's still very colored, and I'll turn the intensity down again, and I get a little better image. It's still not a very good image, partly because of the chromatic aberration. So what I will do next is study the chromatic aberration. I'll put a holder in here and put a filter in, first a red filter, and I'll look through and I'll focus it as accurately as I can, turn the intensity down, and I may even want to cut the diaphragm down, not too small, but to say about half, 3/4 of an inch to get the best image. And I'll focus this as best I can, and I get a focus here, and I'll read that off here. Now you can see in the screen a really quite sharp image. I'm not going to change that for a blue filter and refocus it very carefully. Let's see if we can see that on the screen. I need a little more intensity. And notice it's blurred. But if I move it, I again get a sharper image, showing that the focal point for the blue light is at a different point from that of red, and therefore I can actually get the difference of the index of refraction for blue and red and see the origin of the chromatic aberration. Having studied the chromatic aberration, I can then, let me put the red filter back in here, focus it again sharply as I can. Actually, the quality of the television screen is not good enough to resolve the tiny coils of the filament, although I can resolve them very clearly with my eye when I look in, but you can see the little notch, which is due to a wire holding up the filament, the little cool spot on it. And if I now change the size of the diaphragm, for example, if I take it completely out and turn the intensity down a little bit, notice that the quality is not quite as good. There are 3 little dots on there which correspond to, which are due to reflections of the studio light, but the filament is a little more fuzzed out, and I can't get as really as good a focus with that out as I was able to get when it was in. Now I'll turn up the intensity again, and you can see that that little dark spot is somewhat sharper. If I now close this down, and at the same time turn up the intensity a little bit, I will finally, looking through there with my eye, get to a point where the coils of the filament fuzz out, and that corresponds to the physical optical limit. At that point, I will want to measure the diameter of that aperture, and knowing the diameter of the aperture and knowing the distance from the lens here over to the bulb, I can find out and also knowing the spacing between the coils, I can find out the angle between two adjacent coils. And if I use the expression that alpha, that I can't resolve the coils when the alpha is less than 1.22 times the wavelength of light over this diameter, then I should be able to calculate what the wavelength is, having known what the spacing between the two coils is over there. I'm going to open this up a little bit. Finally, I can study one other kind of aberration. I'll turn this down. And that is the effect of having the lenses off-axis. And if you'll watch the image at the same time that I watch the lens, you can see what happens to the image. If I turn this lens even a very little bit, I get a very badly distorted image. And so one of the adjustments of it that you have to be very sure of in order to get the maximum benefit is to keep this lens with plane perpendicular to the optic axis. So having studied the spherical aberration, the difficulties with resolving power due to the finite wavelength of light, the chromatic aberration, I can also investigate the magnification by measuring the object and image, the object distance here, the object distance there, and the image distance, and use the expression for simple magnifier, magnification to calculate the overall magnification of the telescope. In addition to looking at the particular light source that's provided, namely that light bulb, one can also train the telescope on other objects, either nearby or far away, and study the geometric or optic relations between these two lenses. That's all that's involved in this, but it illustrates most of the principles of a simple telescope.